Hello community! Today we have a beautiful topic. We have a new view on artificial intelligence. So the way we see artificial intelligence changed now. And yeah, in part also to a new startup called Symbolica. Let's have a look. So my first attempt to this paper was easy. I wanted to show you here in the technical description about category theory here, the basic proposition, the definitions here, the algebra that they developed, then go on to here to the pre-sheaves here on function sets. For my green grasshoppers, I would have said, hey, look, by YouTube, you find here Michael Bronstein, here the lecture 3 that I would highly recommend if you are interested in this. And as you see in 10.3 minutes, he introduces here the pre-sheaf concept in mathematics in algebraic topology. So my little green grasshoppers, this is here where you can get your information if you want to start in this. And then we would have gone on with monads. We would have looked at some deeper mathematical framework. We would have come up to here 2 monads, here algebra, homomorphism that we need for this. And then we would apply it simply to large language models. And I thought maybe this is a little bit too challenging for the first run. So I tried a second attempt for this video. And I thought I explain here the main topics. So we are in category theory. This is a new branch of mathematics that studies abstract structures and their relationship. So a category consists of objects and morphism. Morphism between them satisfying certain axioms. And I will show you these axioms. So this theory provides a flexible and compositional framework, allowing here for some uniform description of mathematical structures and their transformation. So a category can be sort of a generalization of sets and functions. The next topic is here Monad algebras. Now, a monad, if you know this, is a mathematical structure in category theory that consists of an endofunctor, so a functor that maps a category to itself, and 2 natural transformation. Natural transformation I will explain later, but just to give you an idea, just mappings between functors. And of course, they also have, as in mathematics, always satisfy specific axioms. Now, monad algebra in this particular context refer to the algebra associated with our monads. And an algebra for a monad consists of carrier object and a structure map that satisfies certain commutative diagrams. And they are particularly useful for describing group action and symmetries. And now you might say, I understand. So we are here in group theory, we are advanced group theory, we are about group action and symmetries that we have in our neural network structures. For example, essential for equivariance in geometric deep learning. Yes, now we start with an advanced mathematical language if you want. Endofunctors, simply a functor that maps a category to itself. In simple terms, it's like a function that takes an object in a category and returns another object in the same category. So they are used to describe transformation within a category. And in deep learning, endofunctors are employed to model various data structures and computation patterns, like lists and trees, and I will show you this in detail. Now, a morphism can also be a parametric morphism. This is kind of a generalization of the traditional morphism in the category theory. And in the 2-category para, a parametric morphism between object A and B consists of a pair where you have a parameter space, and f is simply a function that depends on those parameters, mapping p times a to b. Does parametric morphism allow us to model function with an additional parameter? I will show you this in an example. Now, really important is here if we go a level up. We increase the complexity, a meta level if you want. We talk now about 2 categories. This is a higher order categorical structure in our mathematical framework. And in addition to objects and morphism between objects, which we have the 1 morphism, it has also a morphism between morphisms, so what we call a 2 morphism. And this extra layer of structure enables here a more detailed description of relationships and transformations. In our particular case for neural network, they provide here a framework to study not only the objects and their mappings, but also the relationship between those mappings. So relationships on relationships. We need this for the dynamic in a neural network. And then, of course, we can build an algebra on this. And the next topic is a two-dimensional categorical algebra that we build. This refers to the study of algebraic structures and their properties within a two-category. Of course, what else? Now, notice that in this context, they focus on the commutativity and its variation. And we have a strict commutativity, a pseudo-commutativity, a lax commutativity. I will talk about it a little bit more, and some others. Beautiful. We're almost done. Yeah, lax algebra and coalgebra, I'll give you an example. And then we have free monads and endofunctors. Now, what is it? The simplest way of a free monad is, generated by an endofunctor, is the construction that captures here the iterative application on the endofunctor until it stabilizes. So you can say it's a lift of an endofunctor algebra to a monad algebra. Isn't this beautiful? And of course, we have then also a two morphism and natural transformation. And this is really easy to explain because in a two category, a two morphism are the morphism between one morphisms, so morphism between our objects, and they provide additional relationship and transformation between the mappings in the category, while natural transformation on their particular side are two morphisms between the functors, and they have to obey to certain commutative properties. And they play here a role in defining our monads and associated algebras. And you see, there you have it. A very simple description of some terms that give you an idea where we are currently and what we are talking about. And I thought, okay, it would be great if I could build a story about those topics and I show you how to integrate those terms in what we know currently about artificial intelligence, about neural network, how we build them, how we merge them. And I went here to Cohere, to the Command R-plus model, to the latest model, recording this video. I uploaded the paper, uploaded part of my mathematical server library, and then I ask here R-plus. I ask specific questions, and here are the answers by Command plus, and Command plus is here trying to explain this to you. Maybe you like this way better. Okay, so mathematical foundations of deep learning. You understand? We built here a new mathematical language to optimize our LLM, to get a better insight into the black box, what are neural networks, operational neural networks for us. And we need a new mathematical framework to increase here the performance of the system, to increase here the causal reasoning, to increase here all logical deduction and all logical inference. Finally, the system should work 100%. So, category theory is here, as proposed by the authors of this study, the way forward. It offers here a fresh perspective, as here Cohere writes, a unifying framework for understanding different types of mathematical structures and their relationship. And if we apply category theory to deep learning, we develop a more transparent and expressive mathematical language to describe these complex interactive systems on the layer structure. Beautiful. So we want to improve our LLMs, and we are not anymore in a sandbox playing here with layers and mergers here on an atomic level, but we build a new mathematical framework to understand this. And unfortunately, it's a little bit more advanced mathematical structure. Beautiful. As you can see here in the top right corner, R+, you know, this is AI-generated content. And maybe you like this better. And here we go again with the Monad algebras with equivariance again here to respect the symmetry and the transformation. This is so important. Then about endofunctors here and the data structures and parametric morphism. What else we have? Yeah, then I ask R+ to explain our two categories, the two-dimensional categorical algebra with commutativity and going beyond with lax algebras and coalgebras. And then to build here the bridge now from the theory for the mathematical language to the LLMs. And again here the free monads, the endofunctors in our design of our neural network. So maybe you like this way of presenting it a little bit better. This is here from Cohere Command R-plus, the latest, if you want, open source LLM. And I think it does a great job trying to digest all my data that I provided and come up here with an explanation. Especially when I said here for a case study, so they said, okay, we have an LLM, it's trained on a vast amount of text data, and using now this new mathematical language, we can describe this model as a composition of parametric morphisms, where each layer here is defined by its interaction with specific parameters. And our two-categorical framework allows us to capture this relationship between our neural network layers, including, of course, parameter sharing that we need and all the transformation rules. The model's ability to generate coherent and contextual appropriate responses can be understood, for example, in the simplest case through the lens of equivariance. And here the Monad Algebra provides a way to describe how the model respects certain symmetries in the data, such as semantic equivalence and syntactic transformation. Okay, this is Command R+. And you say, hey, I know this symmetry discussion. Yes, of course. Years and years ago, when we were working with convolutional neural networks, if you read your original paper, you see that in the convolution that were happening, to preserve some rotational symmetry was of utmost importance. And we've chosen specific features exactly for symmetries. And now we find a mathematical language that enables us to have this baked into our mathematical operation. So we do not have to build this up, but we have now a much more elegant, simpler, more powerful mathematical framework for describing exactly this. Okay. So, novel mathematical framework, we get a deeper understanding of LLMs. We can try to describe here their inner workings and refine here the behavior more efficiently. And this new mathematical framework, if you want, is rooted here in category theory. And this gives us some insight. And what we want our LLMs get better in reasoning, causal reasoning, logical inference, and they do not hallucinate, they do not make mistakes, and we want to optimize here our neural network structure. May it be on the transformer level or any other more advanced composition. And having been this far here in the preparation of my video, I thought, okay, how can I do here an attempt for my green grasshoppers? And if you're not into mathematics, and can I shift it to a simplification that you get a feeling for this? This is not a real mathematical description, but this here is my attempt to make it understandable if you are just interested in AI. So I thought here I can try to explain the new mathematical framework as a symphony, because mathematics and music have a lot of common things together. And I thought maybe I'll try it here in an analogon with a symphony. But then I got so hungry thinking about this, so we will start here now with the basic concepts of category theory on a very simple Viennese or Austrian example, a bakery. Yes, we like to have a cup of coffee and maybe a Zimtschnitte. So here we go. What we are talking about in category theory, in the simplest case, are objects. The objects are our fundamental entities that we work with. And in our bakery example, the object could be different types of baked goods. We have a cake, we have cookies, or you have bread in the bakery. Those are all objects. And each object here has unique mathematical characteristics and properties. Now, if we want to have relationship between objects, or what we call mapping between objects, we have this with morphism. In our bakery example here, a morphism could represent the process of baking. So if we have the morphism bake, a cake or bread or whatever, that transform here a raw dough into a delicious cake. So bake would be a morphism from the object raw materials into the object final delicious cake. Now, morphisms have, of course, some rules, some axioms they have to fulfill, like there is an identity morphism. You know this from the classical mathematics. You have to be able to compose here multiple morphisms together. For example, a new morphism combined can be bake and then mix, or bake after mixing, whatever. And there are some kind of associative rules, axioms connected with this. So whatever you have, this is a little bit tricky, because at first the thing here, mix flour and sugar, then mix eggs and mix the liquids. But then I was talking here to somebody who said, oh, if you really bake, there's a difference if you add at first the flour and then the sugar, and the eggs should come in at a certain point. So maybe the example is not perfect, but you know, I just want to show you, we have here the axiom of associativity here, also operating here in our new mathematical framework. So now we are able here to define what is a category. A category is a collection, now we know, of objects and morphism. And those objects and morphisms, they satisfy certain axioms. Pure mathematics. In our simplified bakery example, the objects are our baked goods that you see when you enter the bakery, and the morphism are the processes, or we call it transformation, between them. Category could be named bakery, and it captures the relationship and transformation within here the baking processes. And as I told you, we look at the axioms, and here some axioms here, for example, we have to have an identity, we have to be able to do a composition, and we have the associative rule. Beautiful. Having this, we have now mappings between categories. We defined what are categories, and now we map different categories. Now, the mapping between them, we need a functor. Let's say we have another category called a pastry shop, also very famous in Vienna, which has similar objects and morphism. So, what is a functor in our example? It could be a recipe book that translates the process in the bakery category into the corresponding processing in the pastry shop category. How you bake a bread and how you create a beautiful cake, there are similarities. And this functor preserves the relationship and the transformation between the objects here in a very consistent manner. Plus, we need something else, and we need natural transformation. And they are like interpreters between functors. Here we define functors. Natural transformation gives us simply the interpreters between those functors. So if we have two recipe books, two functors, that translate between the bakery and the pastry shop categories, a natural transformation, very easy, would be the act of interpreting the instruction from one book to the other one. Our goal is consistency and compatibility between the different ways we can apply this to our neural network. Beautiful. Now, if we have a functor that operates within a single category, we give it a specific name. It is called an endofunctor. And in the context of our deep learning now, an endofunctor plays a crucial role in modeling various data structures and computation patterns. If we do all the calculation in our LLM, now we are talking about endofunctors. And they are functions that transform objects within a specific category. In our example, an endofunctor could represent the process of adding toppings to baked goods. It takes an object, such as a plain cake, and transforms it into another object, but within the same category, our bakery shop, like a cake with sprinkles. So, this transformation remains within the bakery category. If we say, okay, now in the bakery category we also have cakes, and it involves adding toppings to existing baked goods. You see, a very simple example, but you get a feeling what this is. Now, they are essential for understanding how data structures are manipulated and transformed within the neural network, within the different layers. And by studying the endofunctors and their properties, we can gain insight into how information is processed and transferred at different layers of our neural network. But now in a complete, absolute, precise mathematical way that we can gain new insight into the working that we do not have right now. Endofunctors also play a role in defining here the algebras and the coalgebras, which are simply mathematical structures used to model the computation and the data structures in a real formal way. So our algebras and coalgebras specify the behavior and the relationship between our endofunctors and the objects. And this is here what provides us here a better understanding of the computation in deep learning. Beautiful. Now you know we have morphism, and now, as I told you, we have parametric morphism. Well, that's easy. So in the introduction of parameters or some additional inputs that influence the behavior of our function or our mapping, you know this. And in the context of deep learning, parametric morphism help us to model the composition and the interaction of neural network layers. How the layers work together. We have hyperparameters, parametric morphism. In our bakery example, a parametric morphism could represent the process of baking a cake with customizable ingredients or decorations. Bake custom cakes, sprinkles, frosting, yes, of course. In the real world of deep learning, the parametric morphism captured the idea that neural network layers often depend on additional inputs or parameters. A layer might perform a specific transformation on the input data, but the nature of that transformation could vary depending on certain parameters or hyperparameters, for example. There's an interlink here to the concept of a two-category, especially to the two-category para. And in para, this is a parametric morphism between object A and B. It's a little bit complicated. Just say, okay, this is here connected to a two-category. And I'll show you an example later on. So, simple. By studying parametric morphisms, we now gain in our new mathematical language, if we apply this, we gain insights into how neural network layers interact and depend on each other. But in a beautiful mathematical way that we can get more insights how we can optimize the structure of our neural network. Great. And now, almost at the end, remember we had Monad algebras, given here symmetry preservation. And Monad algebras provide a mathematical foundation for understanding here the equivariance, which is the property of preserving certain system-wide symmetries or transformation. In our baker example, the Monad algebras can be sort of recipes. You have recipe that ensures the final baked good aligns here with specific property that you want. You have a beautiful fluffy cake, it's beautiful, sweet, and exactly what you wanted. And we need them even if the ingredients or the preparation process undergoes certain transformation. So we make a cake and a Monad algebra for cake baking. This is a little bit strange if I read this, but it's just for demonstration purposes. This would specify the steps and the transformation required to obtain a cake with exactly the desired characteristics. Short example, beautiful. Okay, this specific algebra is a very general algebra, and we can use this in a wide variety of cases. Therefore, I have here 3 additional informations for you if you're interested. If not, skip the next 3 elements. I will leave the example of a bakery, and I will have here the example of a trip. You go on a trip somewhere. In order to understand the elements that we have, that we work with in a Monad algebra, they are objects, or states as we call them, morphisms, you know this now, and endofunctors. Beautiful. So, those 3 elements are important. In our analogy of a trip here, objects correspond to various states of your trip planning. These states could include your current location, your available budget, the items you carry with you, the objects, or even your mood, your state. So each state is a snapshot of your trip at a certain point in time. Now, morphisms now are the action that transition one state to another. We want to have a continuous set of states. So you can move from one city to another, You can change your budget as you spend or save money. You pack or use items from your backpack. You understand what is a morphism. And then we have an endofunctor. And this represents the overarching process of planning and executing the trip now, really. So mapping the trip state space onto itself. And this captures here the essence of the trip evolution. So how each action potentially transforms the trip's current state into a new state. And you say, hey, this sounds familiar to a neural network architecture. And yes, you are on the right track. So the operations here of the Monad algebra, simple, you know this. We have a unit operation, we have a bind operation, as I just told you, and maybe we can do some multiplication depending on the complexity of our system. So a unit operation introduces a new leg of the trip without changing the current state. It's like deciding to take a rest day where your location doesn't change, but the option to start a new activity is presented. So it injects a value into the Monads context, starting a new sequence of operations. A bind operation is simple. It's a crucial operation. Sequences here the legs of the trip, ensuring that the output state of one leg becomes the input state of the next one. Easy. Multiplication is like planning within planning. So if you decide mid-trip to take a side excursion, so a short trip within a long trip, this multiplication ensures that once planned, the excursion integrates seamlessly into the map itinerary. So here we have it. We have monads and the algebra. If you want to look now for a simple explanation, in this analogy, monads act like the special guide for handling task or operation that involves some form of change or uncertainty. And yes, you're right, we have monads also in complexity theory, where we try to describe here a complex self-evolving system. They give us a way to the sequence of tasks, make sure that everything you do is in the right order, and deal with surprises. It's really that simple, like finding a workaround if you're missing an ingredient without having to start all over. So if in a complex system, suddenly you're encountered with a new situation, with a new solution that you found, this is here really helpful. In the algebra, you guessed it, it is simply the rule book that tells us what is allowed, what are we allowed to do with our monads. So it ensures that the starting points are clear, the steps follow a certain pattern, that we have a consistency. You get the main idea. Beautiful. So back now to our main bakery example. And of course, we want to have here the Monad algebra for our neural networks. Context of deep learning, Monad algebra provide a way to describe here the neural network layers that respect here data properties and symmetries. This is so important. So if you have an image classification task, a Monad algebra could specify the transformation operations required to ensure that the network's output remains consistent, even if the input image undergoes a translation, a rotation, or whatever other geometric transformation you encountered with in your real-world examples. So we have now a formal mathematical framework for designing neural network layers that exhibit, for example, in the simplest case, an equivariance or an invariance to specific transformation. So we have here a set of a rule book, or constraints that govern the behavior of the layer, ensuring that it aligns with desired properties. In summary, our Monad algebras, now in our bakery examples, again in the bakery, delicious examples, represent recipes or set of instructions that guarantee a specific property in the final product, in the final baked good, even when the ingredients or the preparation process undergoes transformations. So they kind of provide a mathematical framework for understanding here equivariance and invariance, and these are essential concepts that we have to take care of when we build our neural network and our deep learning processes. Beautiful. Now, the task is to explain a two category. Remember the meta category, the morphism of between morphism. And in a bakery context. The objects, remember, could be types of baked goods, the bread, the cake, whatever you see when you enter the bakery. Now, a morphism or one morphism would be the process or the transformation these goods undergo if you mix them, if you bake them, if you decorate them. Two morphisms then represent a modification or variations of those processes. Remember, meta level. So for instance, altering the baking temperature, the time, can be seen as a transformation from one version of baking to another. And this is exactly why we need here two category. Allows us not to talk just about what baked goods we have and how we can transform them, but also how we can tweak or adjust this transformation themselves if we have new ideas, if we encounter roadblocks and we have to find new solutions. And this is really important, but before I show you why, we have to have the algebra here of our two-dimensional categorical. It involves here studying algebraic structures and operation within the context of the two categories. It focuses on how objects, remember, morphisms, you remember, and two morphisms can be combined. And they have, of course, to obey certain algebraic laws. We are talking about an algebra. Now, in our simple bakery analogon, our algebraic structures, think about it as the set of all recipe and all variation we can apply to our baked goods. Just as in algebra, where we have operations like an addition that combine numbers according to specific rules, in our bakery we have operations now that combine or transform ingredients according to the recipe. This two-dimensional aspect now comes into play when we consider not just the recipe themselves, but also the variation and the modification to those recipes. You see, it's rather simple. In a two-dimensional categorical algebra that we will apply, we're interested in how these recipes and their modification can be systematically organized, combined, transformed, ensuring the entire process here of our raw ingredients to the final decorated product, the decorated cake, adheres to a coherent, structured mathematical framework of transformation and adaptation. We understand what is happening in this damn neural network black box. What a beauty. And for my green grasshoppers, again, the difference between a two-category and a two-dimensional categorical algebra, this is for you. Okay, I told you that I had the original idea before I get hungry to have here this analogon between mathematics and music. So I found that I had here inputted all my mathematical data already into Cohere, into the R-plus LLM. And I said, okay, let's see how good Cohere is now, coming up here with an explanation. So this is now, if you want, a second explanation. If you do not like the bakery example, maybe you like the music analogon. Let's dive into this. And as you can see, Command R+, I reduce the temperature to 0.2 a little bit. A new lens. R+ tells us, hey, I have a new lens of category theory and deep learning. Category theory, a new branch of mathematics, a unique perspectives, a unifying framework. It allows us to understand different mathematical structures in their intricate relationship. By applying category theory to deep learning, we aim to develop a more expressive and intuitive language for describing this complex system like a neural network. And now it's nice because R+ says, hey, let's build this stage for our performance. So what we need the Monad algebras for the equivariance. So the Monad algebras set the stage for our mathematical symphony, and I like this idea. They provide a framework for understanding equivariance, symmetries, fundamental properties that we encounter when we have deep learning, like in our CNNs. Equivariance ensures that the neural network layers respect the symmetry and transformation of the input data. So Monad algebras are like conductors, orchestrating here the behavior of the layers to align with the desired properties, even if the input undergoes some change. Now, what are the players? The players are the endofunctors. Yes, those are versatile players in our symphony. Beautiful. They operate within a category, much like function-like entities, and they help us to model various data structures encountered in deep learning, like a graph structure. Then we have the choreography. And here R-plus says, hey, we have here the parametric morphism and the layer interaction of our neural network. This parametric morphism gives us here a beautiful mathematical framework, a description of a mathematical framework for understanding how the layers work together to transform data, but now in a complete mathematical defined picture. The higher dimension, yes, of course, are the two categories. It's really complex to describe this in a simple example. They bring a higher dimensional perspective, okay? It goes beyond traditional categories by considering not only objects and their relationship, but also relationship between the relationships. This higher order view is essential for capturing the intricate dynamics and transformation within deep learning models. Okay, the dynamics, good. And now for the rhythm. Yeah, we go for the rhythm. Here we have a two-dimensional categorical algebra. Remember, commutativity is here the dominant feature. And in a two-dimensional categorical algebra, we explore the rhythm of commutativity. Okay. Commutativity describes how paths or compositions of layers and transformation graphs relate to each other. Okay, good. Yeah, I go with this. And then we have jazz. We have improvisation happening. And here we have Lex algebras, co-algebras, and computation. Beautiful. But then let's come back here. We have now the final composition. So we go from the mathematical theory to the application in our LLMs. And what we have here, remember, we have the topics of free monads, the endofunctors, and the free monads generated by endofunctors serve as the composer, bringing structure and harmony to our symphony. They establish a bridge here between our endofunctor algebras, which describe the data structures, and the monad algebras, which impose here our rulebook. This connection is crucial for designing neural network architectures, providing a mathematical foundation. I like this. Yeah, two morphism natural transformation, certain properties like parameter update during backpropagation are preserved when layers are composed. Okay, so let's go here to the final performance, understanding here the large language model. Vast repertoire of text data has been pre-trained, fine-tuned, and now our new mathematical language describing this as a symphony of parametric morphisms, where each layer is a unique instrument contributing to the overall melody. The two categorical framework captures the relationship between the layers, including here, of course, parameter sharing. And the model's ability to generate coherent responses is akin to a well-rehearsed orchestra, where our monad algebras ensure that the model respects here the semantic and syntactic transformations. I kind of like the idea that an LLM, like here R-plus from Cohere, is able to follow my ideas, to ingest my mathematical data, and come up with this analogon from a symphony. It's kind of nice that you can personalize the output of an LLM to fit your personal needs, to better understand it, to get a faster access to new topics. Yes, and now finally you know exactly what mathematical framework we need, and now you are excited to read here the original article by Google DeepMind, University of Cambridge, University of Edinburgh, and our beautiful new startup Symbolica AI. And now you will enjoy this because now you have here the basic understanding of this new mathematical framework. Therefore, I hope you enjoyed it, and it would be great to see you in my next video.